Welcome to The Explainer. Today we are decoding a dense, highly academic warning about the very future of global security. We're looking at a technological paradigm shift that is going to completely rewrite the foundational rules of how we keep information safe.
Now, I want you to think of this as a ticking time bomb scenario. Every single day we rely on digital safety. But what actually happens when the ultimate uncrackable code meets the ultimate code-breaking machine? The reality is, our current digital safety, I'm talking everything from your personal banking to classified government data, is about to be shattered by the arrival of quantum computing.
Okay, let's dive into this. We're going to map out this massive geopolitical and technological shift in 5 critical stages. First, our current digital armor. Second, the quantum skeleton key. Then, building the ultimate codebreaker, followed by the national security crisis, and finally, forging quantum-resistant shields.
Starting with part 1, our current digital armor, and frankly, the illusion of absolute digital safety.
Right now, we put absolute trust in modern encryption. It's the invisible shield securing everything from the VPN you use for work to the most highly classified diplomatic exchanges. But to understand why that trust might be a bit of an illusion, we have to look at the machinery. Classical computers operate on bits, right? Data is either a 0 or a 1. It's binary. But quantum computers use qubits. Qubits utilize the mind-bending principles of quantum mechanics, like superposition and entanglement, to exist as both 0 and 1 simultaneously. So quantum computing isn't just, fast math. It's a fundamental paradigm shift that completely shatters our current computational limits.
And that matters because of how our current digital armor is built. Modern public key crypto systems, like RSA, Diffie-Hellman, and elliptic curve cryptography, essentially act as really complex padlocks. They rely on incredibly difficult math problems, like factoring massive integers. For a regular classical computer, picking this math padlock would take astronomically long. We're talking longer than the lifespan of the universe in some cases. So yeah, practically impossible, which is exactly why we feel so safe today.
But that brings us to part 2, the quantum skeleton key and the terrifying reality of breaking the unbreakable.
Because quantum mechanics doesn't just pick the padlock faster, it provides a theoretical skeleton key to bypass it entirely. Now, what's really interesting about this slide is how we look at the 2 major algorithms that do this. You've got Shor's algorithm from the mid-1990s, which targets asymmetric cryptography, things like RSA. Its threat level is an exponential speedup, meaning it renders our current public keys entirely obsolete. On the other hand, Grover's algorithm targets symmetric cryptography, like AES or SHA-256 hash functions. Grover's provides a quadratic speedup. This effectively cuts symmetric key security in half. But the good news there? We can mitigate Grover's just by doubling the key size, say from 128-bit to 256-bit. Shor's algorithm, however, completely different story. That requires entirely new math.
To put a number on that thread, let's look at 2048. An RSA 2048-bit key is the gold standard for uncrackable public key encryption today. A classical supercomputer could never crack it. But a sufficiently large, stable quantum computer running Shor's algorithm, it could break that 2048-bit key in a matter of hours, maybe days.
So, let's move to part 3, building the ultimate codebreaker, the global hardware race. We've got the theory, and we have the algorithms, but now we're looking at an intense engineering race to build the physical hardware that can actually execute these algorithms at scale. And it is absolutely fascinating to see who is in this race and how they're approaching it. We have massive tech giants and totally diverse physics approaches competing. IBM and Google are pushing superconducting qubits cooled to near absolute zero. IonQ is using trapped ions held by electromagnetic fields, which sounds like sci-fi, but it's real. Xanadu is using particles of light in photonic computing. We've also got neutral atoms and even Microsoft researching highly theoretical topological qubits. The immense challenge for all of them, though, is maintaining qubit coherence, basically keeping them stable, and error correction, because qubits are incredibly sensitive to environmental noise.
Let's move to the timeline and see how this builds. Point 1 is where we are right now, the NISQ era, or noisy intermediate scale quantum. We're at about 50 to 1,000 noisy qubits. They're great for research, but they can't break public key crypto yet. Point 2 is quantum advantage, where we're actually seeing machines solve highly specialized problems faster than classical computers. But point 3 is the endgame, the CRQC era, or cryptographically relevant quantum computers. This requires tens of millions of physical qubits to effectively break encryption. Estimates for reaching CRQC vary from a single decade to several decades, but make no mistake, the clock is absolutely ticking.
Which leads us directly into part 4, the national security crisis, or as it's often called, the invisible heist.
This is honestly the most chilling revelation of this entire explainer. The threat isn't just some distant event waiting in the future. It is happening right now. It's called harvest now, decrypt later. Adversaries around the world are currently intercepting and storing vast amounts of our encrypted sensitive data. Sure, they can't read it today, but they are hoarding it with the explicit intention of decrypting it the moment a capable quantum computer is built. Think about the gravity of that for a second. Decades of classified military intelligence, trade secrets, and diplomatic cables are already sitting on servers somewhere, essentially acting as ticking time bombs.
The most immediate and significant threat is the ability of a quantum computer to decrypt vast amounts of previously collected encrypted data. The nation that achieves quantum supremacy first won't just have a really fast computer, they're going to wield unprecedented geopolitical power and an insurmountable intelligence advantage overnight.
And the threat landscape here is incredibly multifaceted. We're looking at the potential for real-time interception of military command and control. Advanced weapons systems could have their targeting and guidance completely compromised. Moving beyond the military, there's the risk of widespread financial fraud, compromised banking, and serious disruptions to global supply chains and power grids, not to mention the massive theft of intellectual property. This is a profound global security crisis affecting everyone regardless of borders, from Wall Street down to the local power grid.
But we aren't completely defenseless. Let's pivot to Part 5, Forging Quantum-Resistant Shields and Post-Quantum Cryptography.
There is an immense amount of hope and energy going into building a new digital shield. Leading this charge is the NIST PQ standardization process. The National Institute of Standards and Technology has been running a really systematic multi-year vetting process. Step 1, they solicited algorithmic submissions from researchers all over the world. Step 2, they subjected these submissions to rigorous global cryptanalysis to really stress test their mathematical hardness. And Step 3, they are selecting and standardizing algorithms proven to withstand both classical and quantum attacks. It is quite literally a global team effort to save our digital infrastructure. And these new shields, they rely on completely different mathematical problems than our old padlocks. We have diverse families of algorithms now. Lattice-based cryptography, like Crystal's Kyber, relies on finding incredibly short vectors in high-dimensional lattices. There's also code-based cryptography, hash-based signatures, multivariate polynomial, and isogeny-based schemes. Now, these new math problems are brilliant, but they do come with trade-offs. They often require much larger key sizes, which means we basically have to adapt our current systems to carry much heavier digital locks. So the crucial point here is something called crypto agility. This is the ability built directly into our digital systems to easily update or replace cryptographic components as new threats emerge. Survival in the quantum era is not a one-time fix. We can't just install a new update and forget about it. It requires continuous adaptation, backward compatibility, and hybrid approaches combining both old and new cryptography to actually keep us safe.
And this brilliantly illustrates the monumental task ahead of us. We know the quantum threat is real, we know the hardware is actively being built, and we have the blueprints for the new shields. But the question I want to leave you with today is this: is our digital infrastructure truly ready to adapt before the quantum clock strikes midnight? It's a massive challenge, and one that will absolutely define the security of our modern world. Thank you so much for diving into this explainer with me. Keep learning, keep questioning, and I'll see you in the next one.